In the heat of Africa stands a large, modern building, shops and offices. Thousands of people passing through every day. Inside, it's always cool, and there isn't a single air conditioner. Not one. How does a 9-story building in a country where afternoon temperatures hit 40 degrees Celsius stay comfortable with zero mechanical cooling? The architect found his answer by watching insects. Air conditioning seems like a basic fact of modern life, but it's one of the most energy-hungry inventions on the planet. In hot countries, it accounts for a staggering share of all electricity consumed. And the hotter it gets outside, the harder it works, and the more expensive staying cool becomes. This building does without it entirely. And the secret to its coolness wasn't born in an engineering lab, it was born in a mound of dried mud, built by tiny insects, an ordinary termite mound. This is the story of termites, an architect who studied them, and a scientific misconception that ended up working brilliantly. It's a story about how inspiration and precise knowledge are two very different things. First, the challenge itself. Cooling a building is expensive and energy-intensive. An air conditioner doesn't create cold out of thin air, it pumps heat outside, and that process burns enormous amounts of electricity. A large building in a hot climate means a crushing electricity bill every single month. Our story takes place in Harare, the capital of Zimbabwe. The city sits high on a plateau, the sun beats down hard during the day. A local developer wanted to build a large, mixed-use shopping and office complex. But air conditioning, something that big, would have cost a fortune, both in equipment and running costs. So the architect was handed a near-impossible brief. A big building, comfortable inside, cheap to run. In plain terms, keep it cool without air conditioning. It sounded like science fiction. The man who took on the job was Mick Pearce, a Zimbabwean architect who grew up right here in Africa. He had always been drawn to buildings that work with nature rather than fighting it with machinery. And so he didn't start looking at other buildings for inspiration. He looked somewhere architects almost never look at the natural world, at structures that have been sitting under the same scorching sun for millions of years and somehow managing without wires or compressors. Termite mounds. If you've ever been out in the African savanna, you've seen them. Towers of compacted clay, sometimes taller than a person. From the outside, just reddish lumps of earth. But inside an entire city of insects, and one of the most sophisticated climate control systems in nature. Here's the thing. These termites are farmers. Deep inside their mound, they cultivate a particular fungus that feeds the whole colony. And that fungus needs an almost perfectly stable temperature around 30 degrees Celsius, too warm or too cold, and the entire crop dies. Meanwhile, outside the mound, the temperature swings wildly, scorching by day, cool at night, a huge daily range. But deep inside, near the fungal gardens, the temperature stays rock steady, as if someone had set a thermostat. No electricity, no wires, no moving parts. How does a pile of clay do what we need entire refrigeration plants to do? The answer lies in its structure. A termite mound isn't solid. It's riddled with channels, passages, and pores, like a sponge or like a pair of lungs. At the time, there was a neat, widely accepted explanation, and it was the one Pearce knew. The idea was that a termite mound works like a chimney. Warm air rising from the insects and fungus drifts upward and exits through the top. As it escapes, cool, fresh air is drawn in from underground passages below. The result was a continuous circulation. Air flowing up through the tower on its own, carrying heat and stuffiness out, drawing cool, fresh air in. A living air conditioner running purely on physics. No plug, no motor. This was the image that caught Pearce's imagination. And something clicked for him. If a mound of dirt can circulate air and regulate temperature on its own, why can't a large building do the same? Instead of cooling rooms with machinery, make the building itself breathe. But an idea alone doesn't become a building. Pearce partnered with engineers from the firm Arup. Together, they set about translating the logic of the termite mound into concrete, walls, and air shafts. The plan was this. The building would draw cool air in at the bottom, push it through its interior, and release warm air out at the top, breathing like a termite mound. And doing it all on almost no energy. And so, in 1996, the Eastgate Centre opened in Harare. Shops, offices, crowds of people every day. A large, modern building. And, as I said, no conventional air conditioning. Step onto the roof, and you'll see the most striking feature. 48 brick stacks rising into the sky like organ pipes. These are the exhaust chimneys. The building's lungs through which it breathes out the warm air it has absorbed. Now for the physics, piece by piece. First, the stack effect. Warm air is lighter than cool air, so it naturally rises. The hot, stale air from inside the building drifts upward through the shafts and escapes at the top. And as it exits, fresh air is pulled in from below to replace it. This is exactly the same principle as a fireplace or a chimney flue. The taller the stack and the warmer the air inside it, the stronger the pull. 48 tall shafts create a powerful flow that draws air through the entire building from bottom to top, no pumps required. To be fair, the building isn't fully passive. There are low-power fans at the base that help push air inside, but these are small, modest units, just giving the airflow a nudge. Compared to a full air conditioning system, they use a tiny fraction of the energy. The second secret is hidden in the walls themselves. Eastgate was deliberately built heavy, lots of concrete, massive floor slabs. Materials like these have enormous thermal mass. They can soak up and store a huge amount of heat while warming up only very slowly. Think of the building's concrete as a sponge, only instead of water, it absorbs heat. During the day, as the temperature inside rises from sunlight, people, and equipment, the sponge soaks up all that heat greedily, and the rooms stay cool. The third and crucial ingredient is Harare's own climate. The city sits nearly 1,500 meters above sea level, so no matter how fierce the midday sun, the nights are noticeably cool. That daily temperature swing is the building's real fuel. What happens at night? As the outside temperature drops, the fans push cool night air through the building. It chills the concrete that has been warming all day, drawing out the stored heat and carrying it away through the roof stacks. By morning, the concrete is cold again, ready to absorb another full day of heat. A closed daily cycle. The thermal mass soaks up heat during the day and keeps things cool. Then the night air discharges it. Over and over, day after day. Put it all together. The building exhales warm air through its stacks, buries the daytime heat in its concrete mass, and flushes it out overnight with cool air. No compressor, no refrigerant, no humming boxes on the facade, just airflow, mass, and cool nights. And this isn't just a nice concept, it works in hard numbers. Eastgate uses roughly 35% less energy than comparable air-conditioned buildings in the same city. Every day, year after year. Less energy means lower bills, which means lower rent for the shops and offices inside. The building doesn't just save electricity, it actually saves people money. There were savings at the construction stage too. There was no need to purchase and install an enormous refrigeration plant, or run heavy ductwork through every floor. The money that would have gone on all that equipment simply stayed in the developer's pocket. No wonder Eastgate became famous. It's held up as a model of green architecture all over the world. Students study it, journalists write about it, architects make pilgrimages to see it. A building inspired by a lump of dirt became a genuine icon. And now the twist that makes this story worth staying for. That elegant image of the termite-mound as chimney that inspired Pearce, it turns out it wasn't entirely accurate. The idea of a continuous updraft warm air steadily rising and exiting through the top was an oversimplification. What actually happens inside a termite mound is considerably more complex. Later, researchers including biologist J. Scott Turner went inside termite mounds with instruments and smoke and saw a very different picture. In many colonies, there's simply no sustained one-way flow from bottom to top. A termite mound functions less like a chimney and more like a lung. Its porous walls allow gases to move in and out freely, What drives that movement is wind gusts from outside and the same daily temperature swings. The air doesn't travel in a loop, it oscillates back and forth, like breathing. In other words, nature's mechanism wasn't what people believed when Eastgate was designed. The building was inspired by a process that, in reality, works quite differently. At its very foundation was a mistake. And here's the astonishing part. The building works beautifully. It has been cool, efficient, and fully operational for nearly 3 decades. How can a flawed understanding of nature lead to such a genuine success? Because Pearce wasn't copying the termite mound line by line, he extracted a principle from it. Let the building itself, its shape, its airflow, the mass of its walls regulate the temperature. After that, real, honest physics took over. And that physics holds whether or not termites are involved. Warm air really does rise. Concrete really does store heat. Harare's nights really are cool. The building rests on those rock-solid truths, not on the finer details of insect biology. That's the key insight. Nature was the spark, not the blueprint. The termite mound didn't hand Pearce a set of instructions. It gave him a direction, a prompt, a what-if. Everything else, the architect figured out and built himself. And there's an unexpected lesson in that. To learn from nature, you don't need to understand it perfectly. Sometimes a half-right idea opens a completely right door. What matters is who walks through it. Biomimicry isn't photocopying nature, it's a conversation. Nature offers a hint, not always precise, not always complete. The human thinks, tests, gets things wrong, and builds. The power isn't in blind imitation, it's in that back and forth, which gives us something strange but important. A wrong idea that points you in the right direction can be worth more than a right idea that leads nowhere. Eastgate is a monument to exactly that kind of productive mistake, and it matters more than ever. Buildings and air conditioners are among the biggest consumers of energy and sources of emissions on the planet. And as the climate gets hotter, we crank up the AC more, which heats the planet more. A vicious cycle. Passive cooling, like in Eastgate, is one way to break that cycle. Using a building's shape, its thermal mass, natural airflow, and cool nights to stay comfortable at a fraction of the cost. And Pearce proved this isn't just a theory, it works in a real, full-scale building, in a hot country, and it's been working since the 90s. That's his whole philosophy. A building shouldn't fight its environment by running machines at full power. It should work with its environment, breathing, warming, and cooling, like a living organism, not against nature, but alongside it. And here's the thought to end on. A building that can cool itself was born from an imperfect understanding of insects. The value of an idea isn't only in whether it's correct, it's in where it takes you. Sometimes, to find the right answer, all you need is to ask the right question. Even if you're staring at a pile of dirt, tiny termites, without knowing it, helped cool a 9-story building in Africa and showed us a way to build without burning the planet. If stories like this are your kind of thing, there are plenty more ahead. Next time, how the humpback whale gave engineers a clue about the perfect shape for a wind turbine blade and an aircraft wing. Until then, keep looking at the world around you and asking, why does that work? Thank you for being with us. If you find the idea inspiring that nature is our greatest teacher, share this story with someone who still enjoys being amazed by the world. We're already preparing the next one, because nature still holds so many secrets waiting to be discovered. See you next time.